On today's lecture number 29, we actually adopt a totally different method. So far, we have been talking about solution methods based on mathematical classification. From this lecture onwards, we are going to simply highlight the scientific and high performance computing aspect alone, and in the process, we basically try to develop high accuracy methods which will by itself be non-dissipative, non-dispersive, and which will have very high spectral accuracy. And one of the candidate method is basically a Hermitian implicit method, which is also known as the Pade approximation that gives rise to what is called as the general compact scheme. So, we are going to talk about compact schemes now onwards, and in the process what we do in this compact scheme is we try to set up auxiliary relations in addition to the differential equations, and we try to obtain the derivatives simultaneously at many points together. And we begin this discussion by talking about the derivation methods for first derivatives, adopting methods with stencils which are essentially symmetric or central, and by using Taylor series analysis, we can set up methods which are called high order compact schemes. This essential idea is to set up implicit relations between the functions and the derivatives, and equating the terms order by order, we can really get very high order compact schemes. We perform a global analysis in the wave number plane for this compact scheme, and we noticed that many of the older compact schemes had some problem with the boundary stencil, and we explain it physically that these problems arise due to stability, instability or overstability at either end of the domain. And we notice that when we have a periodic problem, this does not cause any problem. It is essentially a problem with the non-periodic problem. And as an example, we talk about a 6th order scheme that is due to Lele, and we talk about in general the basis for choosing these compact schemes, because we said that these are auxiliary relations. So, there must be some basis. This relates to what we call as a consistency condition, and there was another way of method that was investigated by Haras and Tassan. They tried to minimize the error as a optimization problem, and they looked at the problem in the wave number space and tried to develop a compact scheme. Let us get to the real core of the subject. When we talked about scientific computing, our intention was to develop methods which will give you accurate solutions. People do talk about high performance computing, and if you have noticed, my first lecture was a sort of a ridicule on that claim. What is high performance computing? We talked about that what people used to do in 80s and used to claim as supercomputing or high performance computing as it is called. We have more computing power today. That does not mean those people who were doing leading edge research those days are doing the same today. There is a mismatch all along. So, instead of talking about high performance computing, we should focus our attention on accuracy, because that is something you can define, right, which is not a fashion statement. Say tomorrow Intel will announce a new chipset, and then we will be calling whatever we did yesterday was not high performance computing. It is not that. So, we try to define everything with the I would say a sobriquet to talk about what is it that we require is basically high accuracy, and that is what you notice that the first point mentioned here is that if you want accuracy, of course, you will have to resolve all relevant spatial and temporal scales, and that is what we decide to do.
And when we do that, we also like to develop numerical methods which does not superpose additional layers of sources of error. So, for example, we by now know with our analysis that numerical scheme must be neutrally stable. We cannot afford to have overtly dissipative solutions which may look good, make us feel comfortable, but the solutions are nonetheless erroneous. So that's not the way we would like to go. We would like completely non-dissipative schemes so that we follow the physics of the problem. The differential governing equation themselves will dictate the accuracy. You don't have to do numerically something, although you may have noticed in yesterday's question paper, last question that I asked was solving the convection equation by a first order upwind scheme and a uniformly second order scheme, and I asked which is better. The answer is the first order, because there you could choose a parameter, the CFL number, n is equal to 1, and then you would get the most accurate solution. That is something happens once in a while for a model equation for model parameters. A priori, we do not know the solution, so we do not know how to select those parameters. So we should not really aim at this 2 that we are seeing. It's not working today. Anyway, the third part is a very, very contemporary part of a discussion. It's a global phenomena that people do advertently or inadvertently compute and get solutions which are plausible, but they are inherently wrong. And this is true of especially in fluid mechanics, when you are looking at high Reynolds number, high Rayleigh number, Kepler number flows, where you see that you have to resolve all those wave numbers, and at high wave numbers, as we have seen, we can invoke dispersion error, and we often have this tendency in the absence of standard solution to view this spurious solutions as to be representing turbulence, and that is one of the disease of the modern day, and we should resist from doing that. So the third point is nonetheless still very important. We need to talk about no spurious dispersion. And somewhere someone have said that you need a high accuracy solution. So basically what you need to do is reduce your discretization error, and one of the major source of discretization error is truncation. And so people try to derive higher order schemes. Higher order schemes by now we know have lesser, so we always try to develop higher order schemes. But as we propose to do in this module of the course, to show that higher order is not synonymous to accuracy always, what should be attempted is to basically classify method based on their behavior in the k space, because that's what we are trying to do. We are trying to resolve k, different wave numbers. So we'll look at in k space and find out how these schemes are doing, and there we would notice, as we intend proving, that classification based on order of truncation error is truly inadequate. We need to do better. Why and how we do it, that is the name of the game in this part. We are going to talk about some extremely high accurate schemes. These are called the compact schemes. They are based on what is called as Pade approximation. And one of the attribute of this method is that you almost get near spectral accuracy while keeping the scheme as compact as possible, right? So that's what we will try to do. Essentially, these compact schemes are implicit in the sense that they relate the derivative with the function in an implicit manner, as shown here in equation 1. For example, let's say we are trying to derive this nth derivative which is shown here on the left hand side with the superscript within the bracket to indicate the order of the derivative. So, this is the nth derivative. They are written in a implicit manner. So, they are not explicitly evaluated pointwise. They are all indicated by the node index here j plus k. K goes from minus NL to NR, and j is the point where we are actually maybe focusing our attention upon. Okay, so what you notice that for nth derivative on the right hand side, we prefer to write it in this way, that h to the power n would be invoked in that fashion, so that this bk, this multiplicative coefficient on the right hand side with the function are pure numbers. They do not depend on grid spacing. Okay, whatever grid dependence comes, that comes through this side. You have already noted that, right? First derivative we always divide by h, second derivative we divide by h square, so on and so forth. So this is a general pattern we would like to do, and to comfort you, to tell you that what we are doing here is not just simply a pedagogic exercise which has rather relevant practical application. Let me tell you that although we are writing this generic equation for a grid with uniform spacing h, but you can actually directly use it for non-uniform grid. What of course you will have to do is you will have to transform your governing equation first. You will have to do additional step there. Whatever the governing differential equation you have in the physical plane or the Cartesian plane, that's what we most of the time write. We transform it into a sort of a computational plane, and in the computational plane we always have uniform spacing. So once we decide to do that, you realize that the scope of such an exercise expand enormously. You can perhaps do almost all possible problems that you have. In fact, I have told you that this method I am teaching you, because even today the flow field around space shuttle is calculated by this method, not by finite element or finite volume method. This has extreme applications, and it has delivered its promise very satisfactorily so far. So let's look at the bandwidth of such a scheme. Bandwidth is determined by how many points across which the derivatives are related, shown by this NL and NR on the left hand side. Same way, we also notice that the bandwidth of the scheme also is determined by the function values. So what we are trying to do, I suppose, let me give you a flavor of the thing that we are trying to do is, let's say we are trying to solve a problem, space-time dependent problem, which we always get. This is a very generic problem that we come across. A vector equation I am writing for say fluid mechanics. This is what we do. This is what is called the Navier-Stokes equation, right? So some of you, most of you are familiar with. But what you notice is that we are talking here of spatial discretization, right? So we are essentially talking about evaluating terms of this kind, right? In the compact scheme, what you do earlier, what we have done, if we had a term like this, we would have written it like this, say ux del del x plus uy del del y. Let's say in a 2D problem, this is how we would be doing, and here we would be writing the vector. So if I do it for x component, I will write ux. If I do it for y component, I will write uy. Now, earlier what we did in explicit method, we specifically wrote those derivatives here, del u x. But here, instead of going through that route, we propose to use this kind of a functional relationship in evaluating the derivatives. So I could set up methods by which I could probably say calculate this kind of derivatives a priori by using this equation given here. So I could do that. Okay. The same way, I could also use the similar sort of scheme by putting this n equal to 2, then I will be getting this kind of terms, right? So there you can do all this. So, basically the compact scheme means we are trying to evaluate these derivatives that we have written here using this equation, and we will do it because it delivers more accuracy. But you can realize that apart from solving the differential equation, you are imposing some additional task on yourself, writing such auxiliary equations. These are not part of the problem, right? This you are doing it to evaluate those derivatives more accurately. And once you do those derivatives more accurately, then you will see the amount of benefit that you derive. So, basically then what we need to do is, for each of these derivatives that we are writing here, we would write out similar equations. And once we do that, we are going to use those. So, once we have evaluated from those auxiliary equations, these derivatives will then go into this equation and plug them there, and that's the whole strategy. So, now you understand how and what way we are going to do. So, that is why the bandwidth is important. We need to find out how many points are involved in evaluating these derivatives via these auxiliary equations that we have written. Now, by now we are familiar that if I would have written a corresponding explicit scheme, I would have probably just simply written like this, right? I am looking at the jth node, I am trying to evaluate the nth derivative. I would have probably just simply written a corresponding equation like this, right? We have written there, right? And we generally go from the bandwidth defines how far we will have to go. We also notice that if this stencil on the right hand side has this kind of a property, what we are talking about here in terms of AK, but suppose if I write here, if the BKs are symmetric, if this quantity is symmetric, then what do we get? We will get a symmetric stencil, right? And that symmetric stencil would not involve the next order term. So, what I am trying to say will become very appropriate if I, let us say, represent it by the derivative, the first derivative. If I do, then you can see the example clearly. What we do here, if we recall that we do it like this, right? So, this is like your second order scheme, and if I am not wrong, you can actually convince yourself what I am writing is correct or not by doing the Taylor series approximation and check that this is a second order scheme, this is a fourth order scheme that we know. What I am saying essentially is about the jth node, the coefficients are symmetric modulus. The sign are opposite. What does it do? Of course, it removes all odd or even. We will remove all the even derivatives, right? So, that is one of the things. If we retain those even derivatives, they would have given rise to numerical dissipation, right? So, we do not want to do it. So, as you see that what we already know from explicit scheme are transferable to what we do with this implicit scheme also. So, on the left hand side, we would require this coefficient A of k should be symmetric about A naught, and furthermore, if we have the bandwidth same, if suppose if I had additional term here, that would have remained unbalanced, that would have given us all kinds of derivatives, and that would not give us a central scheme. So, same way in the compact scheme also, the centrality of the scheme is determined by this condition that AKs have to be symmetric about A naught. and the number of points have to be same on either side of the node under consideration. Now, what requires to be done is to fix this coefficient a k and b k. How did we go about doing this? Of course, what we did was we wrote the Taylor series and equated the coefficient and fixed the coefficients. For example, here you can find out what is B1. B1 is 1 by 2 half, right? B plus 1 and B minus 1 are same in magnitude. One is 1 by 2, other is minus half. And here you can see 1 by 12 and then 2/3, and again 1 by 2. Right? So this is the way that we have done for explicit scheme. We can do the same thing here for the compact schemes too. So better to go and take a look at a specific example. Talk of deriving first derivative in terms of functions, and what we do, perhaps take a case where, let's say, the first derivative is estimated by taking a bandwidth of 2. So it is basically, if we are looking at uj prime, we take 2 points to the left, 2 points to the right on the left hand side, and when we try to relate the functions are what we have written down here, involves 7 points, right? Plus 3 to minus 3, including uj, that will be 7 points. So this is one of many possible ways that one can approach this problem. So view this as a kind of a generic equation. So what happens is in addition to the actual solution of the differential equation, first we will have to do this homework. Given the function right hand side, we are trying to find out what those first derivatives are. That is the auxiliary step that we will have to go through in this exercise. Okay? And as I said, that we have to relate those coefficients by Taylor series expansion, and what we are going to do is, as we write this Taylor series expansion, we will have expressions of various orders on either side, and we try to match those coefficients, and then the first unmatched coefficient that remains, that determines the order of accuracy of the representation. So for example, flip back to the previous page, and if I look at the coefficients of, let's say, uj prime, it will be 1 from here. From this and this, I will get 2 alpha. From this and that, I will get another 2 beta. So the coefficients of uj prime on the left hand side is 1 plus 2 alpha plus 2 beta. Same way, we could expand this individual groups and find out that we would find this is the coefficient of uj prime on the left hand side, this is the coefficient of uj prime on the right hand side. No? So if I satisfy this equation, that means what? We have been very exact up to the first derivative. What is not satisfied is the next order term. So that's why we will call such an equation where we try to evaluate those coefficients by satisfying equation 3 would lead to a second order method. Because what happens, what will be the next term? Next term would be the third derivative, right? So the third derivatives, when I match, then again I will get the next higher order scheme, that is the fourth order scheme. And the coefficients you can actually find out. The third derivative on the left hand side invokes 6 times alpha plus 4 beta, and on the right hand side you get this. You can very clearly see the pattern. This is 2 square, this is 2 cube, and so on and so forth. You can relate that very easily by that specific way of composing that equation too. Now you can go through this exercise, and then you can see that if you match the coefficients up to fifth derivative by invoking the previous 2 equations plus this, then you end up with a 6th order scheme. If you additionally match the 7th derivative terms, then you will get up to their 8th order scheme, and so on and so forth. Now the question is, how many unknowns do we have? We have 5 unknowns, right? A, B, C, alpha and beta. That's what we are trying to find out. So at the most, what we could do is we could satisfy all of these equations, right? All of these 5 equations that we have written so far, 5 equations, 5 unknowns, and then we are done. So we can, in a sense, have a unique 10th order scheme out of this. Okay. However, if you try to, let's say, decide to go for a 6th order scheme, then what you would be solving? You will be solving these 3 equations, right? That is for the second, the first derivative, the third derivative, and the 5th derivative. So this is up to 5th derivative. So we have 3 equations, right? So we have to be then solving for those 3 equations. What are the additional things that we have to do? We'll come to that later. But let's try to see what we do operationally. Let's not just simply talk about what we do in an analysis mode, but what we actually do in computing. In computing, what we are doing here, as you can see on the left hand side, you have the unknown derivatives, which I can write as a vector, and that should be multiplied by a matrix which we are calling as A, and as you have seen, they happen to turn out to be, well, we'll see that constant coefficient entries of this matrix A for the derivatives and B the coefficients of the function. So that's what you will have to do. So you have the computational domain, you would be setting up an equation of this kind, and you'll be evaluating those, each of those derivatives. I'm purposely avoiding to write which derivative it is. Let's say if you are solving a 2D problem, you would have a flow problem, you will have probably 2 components of velocities, and each one will have 2 derivatives, so you will have to solve such 4 equations, 4 sets of equations for calculating del ux del x, del ux del y, del uy del x, and del uy del y. So we'll have to be executing this step for 4 such derivatives. Now this is something I suppose some of you may have difficulty in the beginning to appreciate what we mean by a periodic problem and a non-periodic problem. I think this, despite our various exposure before, let's say we take a domain of this kind and then we have discretized by uniformly spaced point, and the points goes like this. A periodic problem is actually doing it repeatedly on the outside. So this is something again not written explicitly in the book, but whenever you do any computing, you choose a domain, and you are trying to extract knowledge within this domain. How does that knowledge relate to what is happening outside? This is a question that has been sort of bypassed, and people probably do not appreciate. Whatever may be the original nature of the problem, whenever we decide a domain and we do this, we have actually an extension of the same problem for the rest of the universe. It's a periodic extension of that. So that's why what happens is, even though your original problem is non-periodic, and if you solve a problem in a limited domain, or if you increase the domain size, you happen to see quite a bit of difference in the solution. So what is a periodic problem? Periodic problem means if I have, let's say the solution at u at x equal to 0 is u at x equal to 1. This is a physical condition of periodicity of the problem. So physical variables are periodic. What I just now said, that in computation we always have a periodic extension of the computational domain. That's a different aspect. That is what your numerics does. Whether you like it or not, your numerics always do that. This is something you must keep the back of your mind. However, if this condition is not satisfied, if this is true, then this is your periodic problem. So this is what we are talking about, physical periodicity. And if u at x equal to 0, is not equal to u at x equal to 1, then this is what we call as non-periodic problem. Right. So, that is what we are stating here also, that if we have a periodic problem, then I have explained to you many a times before, this A matrix and the B matrix will be periodic. Okay. We have also seen, if I go back to this generating equation 2, if I decide to obtain the derivatives for such a system, you can very clearly see that J can start only from, where can it start from? No, J equal to 4, right, that's good, because you can see, if I try to apply this at J equal to 3, I do not have the information, I am filling out of the domain, right. So, you can see where this choice of the scheme originate is our ability to handle such equation in a most generic fashion. So, there is this problem of compact scheme, although it promises to give you high accuracy, but you have to see that to set up a equation like this, you will have to apply such generic equation only in the interior nodes, and that interior node starts from J equal to 4 here and ends at, suppose I have n points, it should be n minus 4, right. So, that is the whole idea. So, what happens many a times, to avoid such difficulties, you purposely set this C equal to 0. Then you can start the this thing stencil that we have written here from J equal to 3 to n minus 3. So, you can realize that there are so many variations possible, but it also tells you that if we adopt such a scheme, we will have to do something special for the leftover points. Suppose I decide to take 2, then I will have to write a similar equation for J equal to 1, J equal to 2, J equal to 3. From J equal to 4 onwards, we will be using this. The same way, we will have to write out equation for J equal to n, J equal to n minus 1 and J equal to n minus 2, because this equation will be varied from 4 to n minus 3, right. So, you got to realize that the compact schemes have this problem, that if you have a non-periodic problem, then you will have to have additional near boundary stencil. That is what I was explaining to you, that you have to write additional such equations, and those equations are what? You know, because as we are saying that we are restricting our computation in a domain, we have knowledge only about what is happening inside. We do not know what are the states of the variable outside. So, the near boundary stencil, if I want to write it for J equal to 1 or 2 and 3 and so on and so forth, I have to write those derivatives only in terms of what we know. We cannot get information from outside. Then what happens? See, any derivative that I am evaluating here, the information only comes from interior of the domain on this side. What about here? This information also comes from inside. What happens then? When we write down this near boundary stencils, then we are actually imposing some numerical conditionality of the information propagation. On the left hand side, it goes from right to left, and on the right side, it goes from left to right. Suppose I am solving a simple equation like this. You know, that is why we will be looking at this equation very often. This is such a nice equation. This actually sets the gold standard for all computing. If you can't do something with this equation, just go home. Don't waste your time. If you cannot solve this equation correctly, don't hope by any other fancy method life will be easier. what is interesting about this is if C is positive, then what is happening? The information is propagating from left to right. Now, if I use this, what we are suggesting that we need to have a interior near boundary stencil, and this is actually the information is propagating this way, and the numerical condition imposed violates physics. And you would be assured, you will be happy to note that when you violate physics, your numerical method actually blows up locally. Locally, you will see that you are trying to oppose the propagation of the signal in the correct direction. That will immediately hurt you in terms of numerical instability there locally. But having said that, this is something you must realize that in many such exercise, why it does not create catastrophe. Let us say we are trying to solve this equation in a domain like this, and we are setting up some near boundary stencils like this for say this 3 additional nodes on the left, 3 on the side. Then what will happen? Here we are sending the signal from this way, and here we are sending it from there. So, this what we are getting here is non-physical nature of this discretization. Whereas, this aids in the actual physical propagation of the signal, right. We can see that this aids, but we also know from our exam paper yesterday, you have seen that first order upwinding, if you do not choose the NC correctly, you actually overdo it, you can overdo it. So, what happens there? This leads to numerical instability, and this is physical. I will put it in parenthesis, I mean quotes, that physical discretization, it does not violate the directionality, but if you are not careful, then you may end up with lot of numerical dissipation. At the most, you can hope to do it without any dissipation, additional numerical dissipation, but at least it would not do. Now, you may ask me a question, then how come people still do it and get away with it? Well, the answer is right in front of you, because what happens is, apart from the signal itself, the error would also be governed by a equation like this, but with some right hand side that we have established very clearly. Now, what happens is, that means the error also has a directionality that shows that it should go in the same direction as the signal. What happens is, as the error is going to grow here, but it is also convecting. So, after a few time steps, the error which was here, it will be inside beyond this third point, and once they are inside, they are not violating the physical issues, right, physical direction. So, what happens is, this is actually a tragedy of computing, because what happens is, people do this, then they go back and say, look, I am doing direct numerical simulation, because what has happened? You are artificially creating a source of error because of numerical discretization, and that error actually goes inside your computing domain. Once they are outside this bad nodes, they are no more violating the physical directionality, because there your scheme is okay. I mean, you are doing perfectly central scheme. That is why we are looking at central scheme. We do not want to impose additional dissipation. So, from j equal to 4 onwards, you are in a safe territory. So, what happens is, in a problem like this, if I am solving, then I am always, in a spurious sense, I am exciting the system from the left hand side. And the same way, when I am coming on this last 3 nodes, if I am not careful, I am adding numerical dissipation. So, those errors decaying also. So, what happens is, without your knowledge or intent, you are exciting the system spuriously on the left and damping on the right. So, what happens is, if you are solving a problem, you would not require any disturbance, and you would still see as if the flow has been excited. This has, that is what I said, this is a tragedy, because people do not have the proper quantification of what is this additional excitation that we are creating. See, the numerical excitation and the physical excitation in a real physical problem not necessarily going to be the same, right. If I take a different numerical method, I will excite the problem in a different fashion, and in the physical world the background disturbances are probably sometimes not known. You know, my favorite example of tossing a coin, we do not know what are the sources of error there. That is why we will never be probably able to write out a governing equation, evolution equation. If I give you an initial condition, a coin is facing head upwards at this time, at this height, you toss it with this much of force, tell me what will be the outcome when it comes back on the ground. That is the simple problem of tossing a coin, right. Newtonian mechanics, but we still have not seen the end of the problem, right. We do not know what are these background sources, whether we are modeling all possible disturbances or not, we will never be able to know. Now, suppose of course you give it to some people involved in mathematical and numerical modeling, they will always come out with some results, and the paper will be announced in Nature saying that if you face eastward with your left hand tucked in your pocket, the coin will come face head up, right. So, there would be lots of such exciting papers and commentaries of experts, how things are changing. We have now supercomputing ability. So, that is the story. But the point remains that if we are solving a problem, any problem, we cannot characterize the background disturbance. And we do not know, we have not been able to, even today, definitively establish the causality. About causality, I just read 2 days ago, this new theory has been proposed for this large collider. Apparently, the people behind this, they are afraid that it will not work. So, they have said if it does not work, it will prove God exists. It is for the rest of you to figure out what it is. You understand what they are talking about? I don't. Well, they say that some particles called Higgs boson will be created, and the gods do not like it. So, God will not allow this collider to function. Okay? So, that is the end of the story. You prove 2 things, Higgs boson exists, God exists, by non-functional collider in Geneva. That is wonderful research that we do these days. Anyway, we are coming back to this. So, what has happened here, that we create some kind of a numerical disturbance on the left hand side, and we expect that that is going to mimic the physical universe. That is a bit of a sort of a optimism, I suppose. People are optimistic, so we cannot fault them for that. But let me assure you that we do not know the exact relationship between physical disturbance environment with numerical. To expect that all numerical simulation will eventually lead to the same physical results has yet to be proven, right. So, this is something you must realize, that many of the papers that you would be looking at in various journals, they will be saying that we are doing direct simulation, means we do not have to characterize the background disturbance and we will still get the results. Well, I suppose that is yet to be proven, and if somebody does it, that should really deserve sort of credit for that kind of proof. Okay. So, one of the aside of that equation 2 that we have written here that if we somehow decide a priori that we set beta equal to 0, then on the left hand side we have a tridiagonal matrix structure. A is a tridiagonal matrix, and then we already know how to handle that because we have the Thomas algorithm here, and that should allow us to solve this. And well, please, there is a mistake here. So what happens is that in solving this auxiliary equation, you will have to be using Thomas algorithm, and we know if the size of the matrix is n, then we'll be ending up doing 5n to 7n calculations, depending on whether you have a periodic problem or a non-periodic problem. Okay, so let's do a concrete example. So it's better that way. That we set to begin with beta and c equal to 0, so that left hand side we have a tridiagonal structure, but on the left right hand side we have a pentadiagonal structure, right? It's going from j minus 2 to j plus 2. And what you do is write down the Taylor series, equate the coefficients of u prime, u triple prime, and u fifth prime, and then you get these three equations for this three unknowns. Okay, to solve it, you get this unique value. So this is a unique description of the problem. However, you realize that this scheme we can only use it from j equal to 3 to n minus 2. For 1 and 2, with this equation will not work. So is for n and n minus 1. Okay. What you are noticing here, I would like to draw your attention to this, what I call here as a consistency condition. We are in the business of evaluating the first derivative. So come what may, we'll have to satisfy this equation for sure, because that's our basic business, to evaluate the first derivative correctly. So satisfaction of this equation is a must, and that's why we call this as a consistency condition, right? So please do realize that if you are evaluating a first derivative, the coefficients of u prime gives you the consistency condition, which you cannot give up. Okay. Okay. So this is a clear example of how these derivatives can be worked out. You also realize that if you have a periodic problem, then you can use the same stencil for all the points, because you have knowledge of what is outside the domain, so you do not have any problem. So that's why many a times if you are setting up some new method, then do look at periodic problem, because periodic problem helps you avoid this kind of numerically generated issues. Although that becomes little academic in exercise, but it still assures you that you are in the right track, that you are doing it correctly. Okay. So if I now look at the previous exercise, that sixth order scheme that we looked at, the term that is dropped out is proportional to h to the power 6, and that is associated with the seventh derivative. Now, what Lele did, he tried to write it in terms of this. See, you have three equations, right? So if we decide to solve two of the equations and keep one of the coefficients as a parameter, let's call that alpha as that parameter, then basically what we are doing in writing this, we are solving the first two equations, right? And then we'll get the value of a and b like this. So that will be a kind of a fourth order scheme, right? So for the fourth order scheme, a is given in terms of alpha and beta, alpha, and b is also given in terms of alpha. So we can choose different values of alpha, and we can evaluate the corresponding b, and we'll develop a fourth order scheme. Now, if I look at this, there are a couple of issues that comes in the fore, that how do we choose this value of alpha, let's say in this case here. We have seen that if we choose the value of alpha as 1/3, then of course we go to sixth order accuracy. But suppose instead of taking 1/3, if I take 0.3, then what happens? It's not surely a sixth order scheme, it's a fourth order scheme, but how good it is compared to, let's say, if I choose alpha equal to 0.25. or say some value 0.29. Does it mean that these coefficients are some kind of a magic attractor fixed at these points? That means what I am saying, that if I try to write down the error committed so suppose say I try to plot versus alpha the error, and I have a value here alpha equal to 1/3. I know if I choose this, then it becomes a 6th order accurate. My question is, what happens to the error in the neighborhood of this point? Is it a continuous function or a discontinuous function? This obsession with order becomes so much that people will tell you that if you just go little bit to the left or little bit to the right, you have lost the 6th order accuracy and you have jumped down to 4th order scheme. So you may have committed a huge amount of error. But is that true? That's the question that we are asking. The secondly here, that if I look at these discrete derivatives, are they discontinuous functions of this coefficient? This is something we must keep in mind. And you may also like to know, I mean, why should we choose any particular value? Is there any physical basis or not? Now, that's the question that we are posing here in the end, that if we perturb these coefficients from their obtained value apart from satisfying the consistency condition. So, whatever perturbation we do give, the perturbation should still satisfy the consistency condition. You recall that 1 plus 2 alpha should be equal to a plus b, that we have written, right? I think so, if I am not mistaken. Yeah, 1 plus 2 alpha is equal to a plus b. So what I am suggesting to you, that we will perturb all alpha a and b in such a way, but this equation will still be valid. If I do that, what do I get? Do I get a good accuracy, or it is going to be poor? This is something that we would be talking about. Well, there are of course no prize for guessing that this discrete approximation of any derivative is essentially a continuous function. It is not discontinuous, as this sort of supporter of higher order schemes would try to tell you, that if you do not choose alpha equal to 1/3, it is not like, the error is not like this, that you have a point here and then next you have error going like this or going like this. Error does not behave like this. Error has to be, well, it could be still some continuous function like this. It cannot just simply be at one point here and the next point it should be somewhere. It does not happen that way. So that's that. This issue was addressed by these two scientists from Israel, Haras and Tassan. They actually obtained optimal value of alpha a and b to figure out how this numerically established derivative departs from its a very accurate method of evaluating. What we are basically talking about, let us say I have this equation given by this. So, all the spatial derivative is embedded in this, right. So, here a discrete operation with a grid of size I will call that as LH U of H. So, what Haras and Tassan did look at, they set up optimal objective function on the error, that they said, like, suppose I look at this is my exact operator minus the discrete operator. So, this is going to be a function of all these parameters that we have, alpha a b. Now, we try to take that objective function, we try to minimize the error with respect to alpha a and b. those will give me additional equations, right? How many such equations we can generate? 2 only at the most, right? Because we have to still satisfy the consistency condition. That takes away 1 degree of freedom. So you can at the most equate those. That's what Lele was talking about, 2 parameter family. So suppose I fix my alpha based on whatever A and B I get, satisfy the consistency condition, and then I minimize the error with respect to, let's say, A and B. Or that means minimize the error with respect to, let's say, alpha. So basically, the 4th order scheme will have only one condition originating from this objective function. Well, this is something what you may have done in your high school, right? Optimization by looking at the first derivative and the second derivative, you can find it out. So those 2 parameter family that Lele was talking about, single parameter family, essentially gave a 4th order scheme. So everything, the error including, is written as a function of alpha, and we try to minimize that error with respect to alpha, and that closes the system, and you get a optimized 4th order scheme. What Lele did notice, that was a very landmark paper, by the way. Incidentally, alumni of this institute, you would be happy to know, he is faculty at Stanford now, and he did this very important paper that he wrote in 1992, found out that this optimized 4th order scheme actually provides you accuracy that is better than explicit 10th order scheme. And that is the reason, the motive for which we will adopt compact schemes, because this gives you unprecedented access to accuracy. That you would see, if I were to get a 10th order scheme, how many points we will have to take as a stencil if we are taking explicit method? 10th order, so it should be 10 plus 1. You have seen, right? 2nd order you require 3, 4th order you require 5, so on and so forth. If we look at the central scheme, it's always plus 1, right? So he could notice this very interesting thing, that whatever accuracy that you are getting from a optimized 4th order scheme is better than 10th order accurate scheme obtained in an explicit manner. So we basically then come to this observation that the formal accuracy of truncation error is really not the criteria. A better depiction would be looking at in the spectral plane. Now you realize that why we have invested so much of time and effort in learning about waves and spectral analysis. So without that, we would not be able to see all this clearly. So we'll do that. We'll do that systematically as we go along. Okay.